Okay. Okay. So uh, today we'll be talking about vector bundles. So vector bundle informally is 1 second. Yeah. So it's a collection of vector spaces of the same dimension parametrized by a base topological space. So uh, so you have a what's called a total space E, which is the collection of vector spaces, and you have a base space B, and you have a projection from the total space E to the base B, such that the inverse image of any point, say X in the base, is a vector space Ex. So this is a vector space isomorphic to some R to the K. Okay. And what you want is that this collection of vector spaces, locally it should look like a product of an open set in the base with Rk. All right. So let's state the definition formally of what is a vector bundle. So the definition of vector bundle is as follows. So suppose M is a smooth manifold, then a smooth vector bundle over M of rank K is a smooth manifold E together with a smooth map pi from E to M, such that for any point X in M, the inverse image of X, so we'll denote that by E sub X, that this is pi inverse of singleton X. This is a real vector space of dimension K. Okay. So this manifold E, which is called the total space of the vector bundle, it's the disjoint union of these fibers E sub X, which are vector spaces of dimension K. Okay. And what we want is that locally this total space should look like a product. So that means there is an open cover Ui of M and diffeomorphisms phi I from pi inverse of Ui to Ui cross Rk, okay, which sends fibers of the projection here to fibers of the projection onto the second coordinate here. So this diffeomorphism is of the form vector V in the fiber E sub X goes to pi of V, comma, a map phi I, comma, X of V. Okay. So this is of the form X, comma, phi I, comma, X of V, where for each X in Ui, this map phi I, comma, X, this is a linear isomorphism from the fiber E sub X to Rk. All right. So the picture is that we have this inverse image of open set in the cover. This is diffeomorphic to the open set Ui cross Rk. Okay. And this maps under the projection pi to ui, and this also maps under the projection to the first coordinate here. So let me call that P1 ui. Okay. And so this diffeomorphism phi I, this diagram commutes. Okay. So what that means is that the fiber over a point x in ui here goes to the fiber over a point here. Okay, so that gives us this map phi I comma x, which goes to the fiber from the fiber over x. So that is ex to the fiber over x here, which is singleton x cross rk. Okay. And this map is an isomorphism of vector spaces. Okay. For each x in ui. Okay. So this is second condition is called local triviality. That means the vector bundle is locally a product. Okay. Now, once you have this local triviality, then in fact it turns out that the vector bundle, any vector bundle can be obtained from product vector bundles, so trivial bundles, local defined over open sets, products over open sets, by gluing together by certain maps called transition functions. So first of all, this pair ui comma this diffeomorphism phi I from pi inverse ui to ui cross rk, this will be called a local trivialization of the vector bundle E. So now given two local trivializations, ui phi I and uj phi j, we get what's called a transition function. So this is going to be a smooth map gij from the intersection ui intersect uj to glkr, which is the map x goes to. So we have these linear maps coming from the two local trivializations. So yeah, phi ix and phi jx, right? And here we have the identity map. And so here we get a map from x cross rk to itself, right? Which is phi j comma x composed with phi I comma x inverse. Right? This will go from rk to itself, and it will be an isomorphism of rk. So this will be our element of glkr. Okay. So we get a map from the intersection ui intersect uj to glkr. Okay. X goes to gijx. So this matrix valued function gij, this is called the transition function, okay, associated to this pair of local trivializations. And it's easy to see the transition functions satisfy gij x into gjix is the identity map of rk for all x in ui intersect uj. So this product is the matrix product, okay, in glkr. And similarly, gijx into gjkx into gkix, this is also identity of rk. Okay. If I take a triple intersection, ui intersect uj intersect uk. And it turns out these transition functions are enough to determine the vector bundle, namely given any collection Gij from Ui intersect Uj to GLKR, which satisfies these two are called the cocycle conditions, 1 and 2, where Ui is some open cover of M. You get a vector bundle E over M. You can so just given the transition functions, you can define a vector bundle as follows. You take E to be the disjoint union of the products Ui cross Rk, and then you make the appropriate identifications coming from the transition functions. So you identify xv in Ui cross Rk with xgijv in Uj cross Rk. Okay, if X belongs to Ui intersect Uj. Okay, so this will, in a natural way, be a vector bundle over your manifold M, whose transition functions will be exactly the Gijs. Okay. So, any questions? So, to define a vector bundle, often it's just convenient to give the transition functions, because that will uniquely determine the vector bundle. Okay. Okay. So now we need the notion of so I should just mention as an example, we've already seen natural examples of vector bundles. So we can take E to be the tangent bundle Tm over M, or the cotangent bundle T star M over M, or when we were looking at differential forms, then we'll take the kth wedge of the cotangent bundle over M, right? So all of these are vector bundles in a natural way, right? Okay. And what we were interested in are what are called sections of the vector bundle. That means for every point in the base, you choose a vector in the fiber, right? So a section would look something like this. This would be the graph of a section, right? You're choosing a vector at each point, above each point in the base. So the definition of a section is, given an open subset U of M, a section of E over U is a smooth map S from U in M to E, such that this projection pi composed with S is the identity of U. In other words, this means that S of X belongs to E sub X, the fiber for all X in U. So, for example, sections of the tangent bundle will be vector fields. Sections of the cotangent bundle will be one forms. And sections of the kth wedge of the cotangent bundle will be K forms, right? So we can add sections pointwise since they take values in vector spaces, and also take scalar multiples. So the sections of E over U, this forms a vector space, which we'll denote by gamma U comma E. And so these are local sections on an open set U in M. And for global sections defined on all of M, gamma M comma E will denote by simply gamma of E. So now any local trivialization U comma phi from pi inverse U to U cross Rk, this gives an associated local basis of sections S1 to Sk, which are sections on U, where Si of X is what? So at each point you have a linear isomorphism phi x from Ex to Rk. You just take the inverse image of the standard basis vectors E1 to Ek in Rk. at each point. So SI of X will be phi X inverse of EI. Okay. So this will be an element of EX. All right. So if S is a section of E over U, then under this local trivialization, phi composed S of X will be of the form X comma some k tuple of functions A1 of X up to AK of X, right, in U cross RK, where because S is a smooth map and phi is smooth, so phi composed S is smooth. So these functions A1 to AK are smooth functions on U, right? And if I take this local basis of sections S1 to SK, then these map to X comma the ith basis vector EI, right? So that means S I can write as summation over I, AI SI, right? Okay. So that means that these local basis of sections S1 to SK, this forms a basis for the vector space of sections over U as a module over C infinity U, right? We can multiply sections by functions on U, and as a C infinity U module, this local basis of sections forms a basis for the vector space of sections over U. Is that clear? Any questions? Okay. So any local trivialization of the vector bundle gives a local basis of sections S1 to SK such that at each point X in U, S1 of X up to SK of X is a basis of EX. Okay. Now, actually, there is a one-to-one correspondence between local trivializations and local basis of sections. Yeah. So how do we see this? Well, conversely, if I take a local basis of sections, so that means sections S1 tilde up to SK tilde, sections over U, such that at each point X in U, SI tilde of X, I goes from 1 to K, is a basis of EX. Then, first of all, for any I can write SI tilde in terms of my original local basis of sections SI, right? So each SI tilde is sum over J, Aij, Sj, right? Where A capital, these Aij's are, I can think of as the coefficients of a smooth matrix valued function, right? Capital A from U into MKR. Okay. So now the point is, since at each point X in U, SI tilde X and SIX, these are both bases of EX, this change of basis matrix A of X, this is going to be invertible, right? So actually A becomes a smooth matrix valued function on U, taking values in GLKR, right? So this is a smooth map into GLKR. So therefore, pointwise, I can take its inverse and I can define B equal to A inverse. So this is also going to be a smooth map into GLKR. And then once I take the inverse of this change of basis matrix, then I can write the SIs in terms of the matrix B, right? So the SIs are going to be sum over J, Bij, Sj tilde, where Bij's are the coefficients of this inverse matrix B. Yeah. And so now, since I've written any SI in terms of the SI tildes, and we already had that any section I could write in terms of the SIs, right? So then the SIs I'll write in again in terms of the SI tildes. So that means that any section I'll be able to write in terms of the SI tildes with coefficients which are smooth, right? So any S section of E over U, I can write as sum over I bi SI tilde, where B1 to Bk are smooth functions on U. Okay. Is that clear? The point is that these coefficients are smooth, right? That is the point. Therefore, we can define a map using these sections S1 tilde to Sk tilde from pi inverse U to U cross Rk, where we simply send a vector summation over I bi Si tilde x in Ex to the pair x comma the vector B1 to Bk. Okay. And this map is going to be a diffeomorphism because we can write this in terms of our original local trivialization phi. So if I take a vector v in Ex, so v I can write as sum over I ai Si of x. Then each Si I can write as sum over j bij sj tilde x. So then this becomes a sum over ij. Now I take the j outside, interchange the order of summation. So this becomes sum over j, and then inside sum over I bij ai, and then outside sj tilde x. So this becomes sum over j bj sj tilde x, where the vector b is equal to this matrix B transpose into the vector A. Yeah. So that means that if my original trivialization was phi, then if phi of v was x comma a, then psi of v is going to be x comma b, which is x comma b transpose x into a. Yeah. So since phi is a diffeomorphism, it follows that psi is also a diffeomorphism, right? Okay. So we've got a new local trivialization u comma psi, and so therefore we have a one-to-one correspondence between local trivializations phi and local basis of sections S1 to Sk, such that at each point S1x up to Skx is a basis of E sub x. Okay. So is it all right up to here? Any questions? Any questions?
No, sir, it's fine.
Okay. So once you have one vector bundle, then like we saw from the tangent bundle, we could define the cotangent bundle, where each fiber is the dual of the corresponding fiber. So similarly, from a given bundle E, we can define new bundles. So certain bundles will be important for us. So for example, out of these induced bundles, the dual bundle, E star, this is defined to be the union of the duals Ex star over X in M. Okay. So this comes with a natural projection, right, which sends the fiber Ex star to X. And if we have a local trivialization of E, then this gives a chart phi tilde on pi inverse U inside E star. So this maps to U cross Rk star, where I take a dual element alpha in Ex star, and I map it to X comma phi X star inverse of alpha. Okay, so let me just explain here. So for the original bundle E, we had so E star is the disjoint union of the dual spaces. So I need to make this a manifold in a natural way. So we're going to define charts on this. So if I have phi is a local trivialization of E, then this is going to give me a chart on E star, on pi inverse U inside E star, as follows. So for each point X in U, I have a linear isomorphism phi X from EX to RK. So if I take duals, then phi X star, this will be an isomorphism from RK star to EX star. So if I want a map going in the opposite direction from EX star to RK star, I just take the inverse, right? So phi X star inverse, this will be an isomorphism from EX star to RK star. Okay, so this will give me, if I do this for each point X in U, then I'll get my chart phi tilde. From pi inverse U inside E star to U cross RK star. So alpha in EX star maps to X comma phi X star inverse of alpha. Is this clear? Okay. So I can, so this map will be a bijection, and then I can use these bijections to define a topology on E star by declaring these phi tildes to be homeomorphisms, so that, you know, if I have a point in E star, then a basis of neighborhoods of that point will be given by taking the inverse image under phi tilde of a basis of neighborhoods in U cross RK star. Okay. So that will define a topology on E star. And then it's not hard to see that this topology is well defined, because if I take another local trivialization U comma psi of E, I get an associated chart psi tilde from pi inverse U in E star to U cross RK star. What will the change of charts be for these two charts, phi tilde and psi tilde? So I have to look at psi tilde composed with phi tilde inverse of a pair X comma beta, where X is in U and beta is in RK star. So by definition, this is going to be psi tilde of phi X star of beta. Okay. So note that phi X star goes from RK star to EX star. Okay. So phi X star beta is an element of EX star. And psi tilde applied to this will be X comma psi X inverse star applied to phi X star of beta. So this is going to be x comma phi x composed with psi x inverse star of beta. Okay. And this map phi x composed with psi x inverse, this is nothing but a transition function, right? This is a transition function for the pair of trivializations phi and psi. Okay, this is a transition function for the vector bundle E, and then I'm taking its dual, okay, pointwise. All right. So the transition functions are smooth functions of x. So this is going to be a smooth function of x and beta. And so this change of chart psi tilde composed with phi tilde inverse, this will be a smooth map from U cross RK star to itself. And therefore I can use these charts to define a smooth manifold structure on E star. Okay. So E star will become a vector bundle over M. Okay, with local trivializations, these phi I tildes taking values in Ui cross RK star. And the transition functions, as we've seen above here, Gij tilde will be Gij inverse star. Okay. From Ui intersect Uj to GLK of RK star, to GL of RK star. Is this okay? Any questions? Yes, is this all right? Yeah.
Yes, sir, it's fine.
Okay. Okay. All right. So we can define a dual bundle to any vector bundle E. So that will be important for us. Also, we will need what's called the tensor product of vector bundles. So given vector bundles E and F over M, we can define a vector bundle E tensor F over M, where the fibers are going to be the pointwise tensor product of the fibers EX and FX. Okay. And local trivializations will come from the local trivializations of the bundles E and F. Okay. So suppose E is a vector bundle of rank K. So the trivialization takes values in U cross RK. And F is a vector bundle of rank L. So the trivialization takes values in U cross RL. Then at each point, right, we have a map, a bilinear map from the product of the fibers EX cross FX to the tensor product of RK with RL. What is the map? It is V comma W goes to phi x V tensor psi x W. Is this clear? So this is bilinear in VW. Therefore, it induces a linear map, right? By the universal property of the tensor product, any bilinear map is going to induce a unique linear map, right? Which we denote by phi x tensor psi x from EX tensor FX to RK tensor RL, right? And this is going to be an isomorphism because it maps a basis of EX tensor FX to a basis of RK tensor RL. All right. Okay, so this is going to be an isomorphism with inverse phi x inverse tensor psi x inverse. So that's going to be a linear map from RK tensor RL to EX tensor FX. So we can take tensor product of linear maps, right? That will be a linear map between the tensor products. Okay, so let me stop this session and start a new one. All right. Okay, so let's continue. Okay, so point-wise, given the tensor product of the fibers Ex and Fx, we get an isomorphism phi x tensor psi x from Ex tensor Fx to Rk tensor Rl. Right. So point-wise, we get these maps. So as X ranges over U, we get charts which are going to map into U cross Rk tensor Rl. Okay. So as before, we can use these to define charts on the tensor product E tensor F. Okay. That will be the disjoint union of the fibers Ex tensor Fx. All right. And the change of charts is easy to see that the transition function for E tensor F is going to be given by what? Phi jx tensor psi jx composed with phi ix inverse tensor psi ix inverse. So here phi j and phi I, these are two local trivializations of E, and psi j and psi I are two local trivializations of F. And the transition function for E tensor F is going to be given by this composition. So this is just going to be given by phi jx composed with phi ix inverse tensor psi jx composed with psi ix inverse. So in other words, it's just the tensor product of the transition functions Gij for E tensor with Gij for F. All right. Okay. So that is the tensor product bundle. Okay. And now we need another bundle which will be useful for us, which is called the pullback bundle. So this is defined as follows. Suppose F from M to N is a smooth map between smooth manifolds M and N, and let E be a vector bundle over the image, over the target manifold N, okay, with the projection pi from E to N. Then we can define a vector bundle called the pullback bundle of E under F. So F upper star E. This will be a vector bundle over M. Okay. So how is this defined? So F upper star E, this is defined to be the set of pairs X comma V in the product M cross E, such that F of X is equal to pi of V as an element of N. Okay. So F takes values in N and pi takes values in N. So we want Fx to be pi V. Okay. And what will the projection map for this F star E be? It will just be the projection onto the first coordinate, X comma V goes to X. Right. So for this projection, what will the fiber of a point X be? Well, if I fix X, then I'm just looking at the set of V such that pi V is equal to Fx. In other words, I'm looking at the fiber of E over the point Fx in N, right? So the fiber of F star E over X, this will be singleton X cross E sub Fx. Okay. So this I can identify with the vector space E sub Fx. Okay, so the pullback bundle is a bundle where over each point X, you take the fiber of E over F of X. Okay. So for example, Suppose say M is a circle and say N is a sphere. And F is a map from the circle into the sphere. Now, now the image of F, it's possible F could be an embedding, all right? F could be an embedding like this. So this is an embedded circle inside S2. Right, this could be the image F of M. So if it's an embedding, then all we're doing is we're taking the fiber over each point F of X, right? And in other words, you can think of the pullback bundle in this case where F is an embedding, it's just given by restricting the bundle on the whole space. N, you just restrict it to the image of F, right? But that is not necessarily always the case. So F need not be an embedding. The point of the pullback bundle is that this makes sense even if F is not an embedding. So, for example, F could be a figure 8 like this. So it's not an embedding. All right. So there would be points here which map to the same point in N. Okay. So the pullback bundle will be given by taking the fibers along the curve and pulling them back to the domain of the map F. Okay. So in this case, it's not given by a restriction, right? It's not given by restricting the total bundle to the image of F. Okay. Right. So the point of the pullback bundle is that F does not have to be one-to-one. It does not have to be an embedding. All right. Is this clear? Any questions? Okay, so the fiber of the pullback bundle over X is the fiber of E over Fx. Okay. So is the definition of the pullback bundle clear? Yes? Okay. So we have to see that this is locally trivial, right? We've defined a bundle. I mean, the fibers are vector spaces, the fiber of E over F of X. How do we get local trivializations, right? So we'll get local trivializations as follows. So suppose V is a V comma phi is a local trivialization of E over N, okay? So phi goes from pi inverse V inside E to V cross RK. So then take any open set U in M such that F of U is contained in V. So for example, you can take U to be F inverse of V, all right? So this is an open set in M. So then we define a local trivialization phi tilde of the pullback bundle. So this is going to go from P inverse U inside F star E to U cross RK. So I take a pair X comma V. So recall that here, by definition of the pullback bundle, X is a point in U and V is a point in E sub Fx. So here Fx belongs to the open set V in N, right? Therefore, I can take the trivialization of E over N and apply it to the vector V, right? So I can look at this x comma v mapping to x comma phi sub fx applied to v. Is this clear? So this is going to map the fiber of f star e isomorphically to rk, right? Is this clear?
Yes, sir.
Yeah. Okay, so this will be a local trivialization for the pullback bundle. And what will the transition functions for the pullback bundle be? Well, the transition function gij for f star e, this is going to be what? This isomorphism phi j x tilde composed with phi I x tilde inverse. So what is this? This will be phi j at the point f of x composed with phi I at the point f of x inverse. So when I compose these two, I'll just get the transition function for the bundle E evaluated at the point f of x, right? Okay. So that means the transition functions for the pullback bundle, gij of f star e at a point x is gij of e at the point f of x. All right. Is that clear? Okay. So these are the transition functions for the pullback bundle. And finally, what are sections of the pullback bundle? Well, suppose S is a section of the pullback bundle f star e over an open set U. So what does it mean to be a section of the pullback bundle? That means any point x in U maps to some point S of x in the fiber of f star e at x. So S of x is a point. So the pullback bundle is a subset of M cross E. So S of x is going to be a pair x comma sigma x, where x belongs to M and sigma x is in E. And this is in the fiber of the pullback bundle. The fiber is singleton x cross E sub fx. So that means nothing but that this sigma of x belongs to the fiber E sub fx. Right? So in other words, a section of the pullback bundle S, these are in one-to-one correspondence with map sigma from an open set in M, U in M, to the total space E, such that sigma of x belongs to the fiber E over f of x. Okay. So that is a section of the pullback bundle. So is that clear? So where do we see sections of the pullback bundle? Well, we will see them naturally when we take deformations of maps. So suppose I take a, like when we were looking at the prism operator, we were looking at homotopies, right? So suppose I have, say HT. This is a smooth family of maps from M to N, all right? Where mod T is less than some epsilon. And let me call H0 equal to a map F from M to N. Yeah. Then, so for example, M could be the circle. This is say M. And say this is N. And my homotopy of maps, maybe it looks something like this. These are my maps. Okay. HT. Okay. Now what can I do? Now I take a point X in M. So that gives me a curve in N, namely I fix X and I look at the curve. So if I take an X in M, then we get a curve gamma sub x from the interval minus epsilon epsilon into n, t goes to ht of x, right? This is a curve in n. So it will be this curve here, okay, right? So what I can do is I can differentiate this at time t equal to 0. So then that will define for me sigma x. This is defined to be del t at t equal to 0 of ht of x. Yeah. So this is what, when I differentiate this at time t equal to 0, what am I going to get? I'm going to get a tangent vector to this curve at time 0, right? At time 0, it takes the value h0 of x, which is f of x. So I'm going to get a tangent vector at f of x, right? So this is going to be an element of the tangent space at f of x to n, right? Is this clear? Yes. Okay. So in other words, this gives me this sigma. So this is a map from M into the tangent bundle of N, right? X goes to sigma x, which is an element of, so this is del t at t equal to 0 of ht of x. So this belongs to the tangent space at f of x of n, right? So if this was my f here, this curve, then I'll get a what's called a vector field along f. So that means at each point in the domain, I'll get a tangent vector at f of x. Okay. In other words, this corresponds to a section of the pullback of the tangent bundle of n. Is this clear? Right? Yes?
Yes, sir.
Okay, so a homotopy, if I take a homotopy of maps and I differentiate at time t equal to 0, then I will get a section of the pullback bundle, the pullback of the tangent bundle of n. Is this clear? So this is why the pullback bundle is useful. All right. Does this make sense? Yes?
Yeah.
All right. Okay. So, yeah. So this, a section of the pullback of the tangent bundle, what is it giving me? It's giving me a way to deform the map F, right? It's giving me a direction at each point in which to deform the map F, right? Is it clear? Right. Yeah, so in this picture, let me just make it clearer. This will be, say, F, right? And then at each point, you have this tangent vector. This is sigma of x. Is this clear? So this gives you a way to deform the map F, right? You move in the direction of sigma x at each point. That will give you a deformation of F. All right. Yes? Okay. So notice that even though if I look at the space of maps from M to N, that is a nonlinear space, right? But what we're doing is taking a linearization, if you like, by looking at the infinitesimal deformations of the map F. That is a linear space. That is the vector space of sections of the pullback of the tangent bundle, F star of Tn. Does this make sense? Okay, the space of infinitesimal deformations of F, that is a linear space. That is a vector space. It is the vector space of sections of F star Tn. Does this make sense? Yes?
Yeah.
Okay. So this gamma of F star Tn, this is equal to the vector space of infinitesimal deformations of F. All right, is this clear? Yes?
Yes, sir, it is clear.
Okay. So if you like, the space of maps from M to N, that is, in a sense, some sort of infinite dimensional manifold. And the tangent space to that manifold is, if you like, heuristically, it is the this space of sections of the pullback F star Tn. All right. So you can think of this. This is some infinite dimensional vector space. Heuristically, this is something like the tangent space at F to the manifold of maps from M to N. Make sense? Yes? Okay. Yeah. Does this make sense?
Yes, sir.
Okay. Yeah. So that's why the pullback bundle is useful, right? You can use it to look at infinitesimal deformations of maps. Okay. Okay. All right. So now we can come to the next topic, which is connections on vector bundles. Okay. All right. So before giving the definition, let me give some motivation, right? So what is a connection on a vector bundle? So connections on vector bundles. Okay. So informally, a connection so these are denoted nabla on a vector bundle E over M. This is supposed to give us a way to differentiate sections of E. See, what is the point? The point is So suppose I take a curve in M, okay, and I'm looking at, say, fibers along that curve, okay, and I take two nearby fibers, right? So this is, say, P, and this is Q, okay, and I have the fiber EP, and I have the fiber EQ. Okay. Now, if I have a section, right? So it's some vector here at P, and it's some other vector here at Q. I want to differentiate this section, right? I want to be able to differentiate this section. The problem is that this section at different points, it takes values in different vector spaces, right? So I cannot add or subtract the value. I cannot subtract the values of S at Q and S at P, right? Because they take values in different vector spaces. So we need some way of identifying these nearby vector spaces, these nearby fibers of the vector bundle. Okay. And actually what a connection is going to do, it is not going to a priori identify nearby fibers. It is going to identify infinitesimally close fibers. Okay. So what a connection does is it identifies giving a way of it gives a way of identifying infinitesimally close fibers E of X, well, or E as in this picture, EP, EQ with Q infinitely close to P. Okay. All right. So what does it mean to identify infinitesimally close fibers, right? Okay. Well, what it means is very simple. We're just going to give a way to differentiate any section in the direction of any tangent vector, say V, to the base. Okay. So if I move along any direction in the base, then I should be able to differentiate my given section along that direction. Okay. So what does it mean to move along any direction in the base? That means I can look at a vector field on the base, right? So I look at an element of chi-m. Okay. And I want to differentiate sections. So I look at gamma of E, the space of sections. Okay. So then a connection is going to be a map from chi-m cross gamma E to gamma E, a vector field X together with a section S. This goes to a new section, which will be, you think of as the directional derivative of S in the direction of X. Okay. Nabla sub X of S. So it's just going to give us a way of differentiating sections. So this should be a differential operator, this nabla. So it should satisfy the Leibniz rule. Okay. So it should be linear and satisfy the Leibniz rule. So that is what we're going to take as our definition of a connection. So it's going to be a map from chi-m cross gamma e to gamma e, x comma s goes to nabla xs, such that, first of all, nabla x sub s, this is R linear in S for a fixed x. Okay. So if I multiply S by a scalar, then that scalar comes out. And if I take nabla x of S1 plus S2, that should be nabla x S1 plus nabla x S2. Secondly, it should be C infinity M linear in the vector field X for a fixed S. Okay, so that means it should be linear in X, but not just linear with respect to constants, but linear with respect to functions on M. Okay, see, a vector field X on M, I can always multiply by a function F on M, right? So this C infinity M linear means that nabla of Fx applied to S, the F will come out. It will be F times nabla X of S. All right. Okay. And thirdly, we should have the Leibniz rule, right? Acting on sections, this should be a differential operator for a fixed X. So the Leibniz rule will be that nabla X of F times S, where F is a smooth function on M, S is a section of E. This should be, so first you apply X to the function F. So this will be XF into S, all right? Plus, then you apply X to the section S, F times nabla X of S, all right? So this is the Leibniz rule. Is this clear? Okay. So a connection will just be a map satisfying these three properties, all right? Is this clear?
Yes, sir.
Okay. So how do we get a section for a connection, for example? So suppose S1 to Sk is a local basis of sections on an open set U in M. Okay. And I take phi is a smooth function with compact support in U. Okay, so a bump function supported in U. Now, for any S, a section on E, a section of E, if I look at phi times S, then phi times S, this is supported inside U, right? Because phi has support contained in U. So phi times S, I can write as sum AI SI, because the SIs are basis of sections on U, right? So phi times S, I can write as summation AI SI, where A1 to AK are smooth with compact support in U. Then we define nabla X of S to be the sum over I X AI into SI. Okay. So this will again be a global section because the AIs have have compact support contained in U. So X of AI will also have compact support contained in U. Okay. So these will be globally defined. All right. Is this clear? And it's not hard to see that this defines a section, right? This defines a connection, sorry. So first of all, it's linear in S, right? It's real linear in S, right? Because if I take S1 plus S2, then phi times S1 plus S2 will be, you know, if phi times S1 is, well, okay. This is quite simple to check. I mean, so okay, the one thing you have to check is the Leibniz rule, right? So the one thing you have to check is the Leibniz rule. So that's simple because if I take F times S, then F times S will have coefficients F times AI, right? Yes. Okay. So my nabla X of Fs, this will be the sum over I, X of FAI, right? And then X satisfies the Leibniz rule. So x of FAI will be XF into AI plus F into XAI. And so that will give you the Leibniz rule for this. Is that clear? Yes? Okay. So why is this example useful? Because this gives us a connection from a local basis of sections, okay, on an open set U. But then we can cover the whole manifold by charts of local trivializations, right? And then on each chart we can define such a connection, and then it's easy to see that linear combinations of connections are connections. So so using a partition of unity, we can add together these connections to get a connection on the whole manifold. All right. Yeah. So that will give you existence of connections. All right. Is that okay? Yeah. Okay. So, all right, let me not, there's just about 2 minutes left. Before starting this next proposition, are there any questions?
No, sir.
Okay. Okay, so let me just state what this next proposition is saying. The first thing is that a connection is a local operator. So if I have vector fields x1 and x2 and sections s1 and s2, such that x1 is equal to x2 and s1 is equal to s2 in a neighborhood of P, then the value of the connection at P is equal for these two. All right. Okay, so the connection only depends on, if you like, the germ of X, the vector field X near P, and the germ of the section S near P. All right. Okay. All right. So let me stop this session and start a new one. Okay. Okay. All right. So this next proposition says that a connection is a local operator. So it only depends on the germs of the vector field and the section near a point P. And secondly, using the first part, you can see that a connection on M is going to induce a connection on any open set U in M. So that's going to be a map from vector fields on U, chi U, cross sections on U to sections on U. Okay. Where this induced connection on the open set U, this is compatible with the connection on M, in the sense that if I take X as a global vector field on M and S is a global vector field of E, a global section of E, sorry, then nabla X sub S restricted to U, this is given by the induced connection nabla of X restricted to U applied to S restricted to U. Okay. So any connection on the whole manifold M induces a connection on a compatible connection on any open set U in M. Okay. Okay, so let's first see part one, that the connection only depends on the germs of X and S near P. So let U be a neighborhood of P such that X1 is equal to X2 and S1 is equal to S2 on U. So let V be an open neighborhood of P whose closure is contained in U. And let F be a smooth function with compact support in U such that F is equal to 1 on V. All right. So this is possible because V closure is contained in U. All right. So then if I look at F times X1 minus X2, this is identically 0, right? Because inside U, X1 is identically equal to X2. So this is 0 inside U, and outside U, F is 0. So this F times X1 minus X2 is 0 outside U as well. So this is a global section which is identically 0. And similarly, F times S1 minus S2 is also identically 0. Okay. Therefore, by linearity of the connection, right, since the connection is linear, the 0 vector field will map to 0. So 0 will be equal to nabla sub F times X1 minus X2 applied to S1 at P. And now we can use the fact that the connection is C infinity M linear. So this function F will come out. So this will become F at P into, and then it's linear in the vector field. So this will become nabla X1 S1 minus nabla X2 S1 at P. And F at P is 1, right? Since F is 1 in this neighborhood V of P. So this will become just nabla X1 S1 at P minus nabla X2 S1 at P. Okay. So this difference is 0 means that these two are equal. Okay. So this tells us that the connection only depends on the germ of the vector field X near P. Is that clear? Right. If X1 is equal to X2 in a neighborhood of P, then nabla X1 of S1 will be equal to nabla X2 of S1 at P. All right. Yes. Similarly, using the Leibniz rule, we can see that the connection is only going to depend on the germ of the section near P, because we have 0 is equal to nabla X2 of F times S1 minus S2 at P, because F times S1 minus S2 is identically 0, right? So since nabla is R linear in the second variable, applied to the 0 vector, it's going to give you 0, right? So now you use the Leibniz rule. So by the Leibniz rule, this will be X2 applied to F at P into S1 minus S2 at P plus F at P into nabla X2 of S1 minus S2 at P. But now F is, well, S1 minus S2 is 0 at P. So this first term vanishes. And the second term, F of P is 1. So this will become, just by linearity in the second variable, this will become nabla X2 S1 minus nabla X2 S2 at P. So that tells you that nabla X2 of S1 is equal to nabla X2 of S2, right? So putting these together, you get that nabla X1 of S1 at P, this is equal to nabla X2 of S1 at P, and that is equal to nabla X2 of S2 at P. All right. So that proves the first part. Okay. Yes. Okay. And once we have this, then we can define the connection on any open set. So suppose X is a vector field on U and S is a section on U and P is a point in U. So you let phi be a smooth function with compact support in U such that phi is 1 on a neighborhood of P. Then phi X and phi times S, these are globally defined sections, right? Which vanish outside U. Okay. Therefore, we can define nabla X of S at P to be nabla sub phi X applied to phi S at P. Okay, the point is the right-hand side here is given by the connection on the whole manifold M acting on this global vector field, this global section phi s applied by this global vector field phi x. Okay. And this is well defined because if I take a different function phi, but I mean, any such function is one on a neighborhood of P. So the germs of phi x and phi s near P are equal, right? Independent of the function phi. Okay. So by part one, this is well defined. Is that clear? Okay. So in fact, this connection is given how? That nabla x applied to S, nabla x of S is nothing but nabla x tilde S tilde, where x tilde is any global vector field in chi-m and S tilde is any global section in gamma e, such that x tilde is equal to S and S tilde is equal to S in a neighborhood of P. That's all, right? Okay. So then it's easy to see that this defines a connection on the vector bundle restricted to U. Okay. And it's clearly compatible with the connection on all of M. Okay. So is this all right? Yeah. So we can localize the connection. All right. That's the point of this proposition. The connection only depends on the germs of the vector field and the section. And now we can define what are called the Christoffel symbols or coefficients of the connection. So suppose we take a local basis Si of E on an open set U. Okay. And suppose x1 to xn are local coordinates on M. Okay. So they take values in Rn. Okay. Then if I look at, so I know that I have a connection, an induced connection on U, right? I have an induced connection on U. So then I can look at nabla del xi of Sj, right? This makes sense because del xi is a vector field on U and Sj is a section on U. So this is going to be, again, a section on U, but any section on U is a linear combination of the basis, the local basis of sections, Si. So this I can write, therefore, as a sum over K, some coefficients, gamma ijk into Sk, right? Where gamma ijk's are smooth functions on U. Okay. So these gamma ijk's, these are called the coefficients of the connection with respect to this local basis Sj and the basis of vector fields del xi. All right. So these coefficients of the connection allow you to compute the connection applied to any section with respect to any vector field as follows. So if S is a section on U and X is a vector field on U, I can write S as summation over J, Aj, Sj, and I can write X as sum over I, Bi del xi. Okay. Then for any point P in U, we can compute nabla X S at P. So I write S as summation Aj, Sj, and I write X as summation Bi del xi. Then by linearity of the connection, this is going to become a sum over Ij, nabla sub Bi del xi applied to Aj, Sj at P. And now I use that the connection is C infinity M linear in the first variable. So this Bi is going to come out. And then I'll have nabla del xi of Aj, Sj. So by the Leibniz rule in the second variable, this will become del Aj del xi into Sj plus Aj into, and then I'll have nabla del xi of Sj. That by definition is the sum over K, gamma ijk Sk, right? So then it's just a matter of grouping together the terms. Okay. And finally, you get this following expression that nabla x of s is going to be the sum over k, the local basis sk into these following coefficients: sum over I bi of p del ak del xi of p plus sum over ij bi of p aj of p gamma ij k of p. All right. Is this clear? Yes. Okay. So notice that the value of this nabla xs at p, this only depends on the coefficients bi of p, right? If I fix s, then as a function of x, the vector field, it only depends on the coefficients of the vector field at p, right? These bi of p. Yes? It does not involve higher derivatives of bi. It only involves the values of the bi's, right? That means this only depends on x at p, right? Which is sum over I bi of p del del xi at p. Is this clear? Okay. Yes?
Yes, sir.
Okay. So therefore we can then define in the first variable, we can localize the connection to a point. In other words, this vector field x, I can actually replace by a tangent vector. Right? How? Well, you take any open set U in M, and you take any section S on U, and you take any point P in U, and you take any tangent vector V in TPM. Then you define nabla sub V of S. You define this to be nabla sub X of S at P, where X is any vector field on U such that X at P is equal to V. Okay. Then by the calculation that we've done here, this is well defined, right? Because this derivative here, I mean, this value of the connection, it only depends on X at P, right? Is this clear? Yeah, so in the first variable, we can just reduce the vector field to its value at a point. Okay. We can localize at a point. So it doesn't even depend on the germ of the vector field near P. It only depends on the value of the vector field at P. Is that clear?
Yes, sir.
Okay. All right. Okay. So this is going to be useful because now we are going to use the connection to do what we wanted to initially, which is identify nearby fibers of the vector bundle. So this is going to be possible using something called parallel transport with respect to the connection along curves in the manifold M. Okay. So how do we define parallel transport along curves? Okay. So suppose gamma is a smooth curve in M. So then we first define what is a section of the vector bundle along gamma. So this is a map sigma from the same interval of definition of gamma into the vector bundle such that sigma of t belongs to the fiber at gamma of t. Okay, for all t and I. In other words, you can think of sigma as a section of the pullback bundle, gamma star E. All right. So this is a section along gamma, along the curve. Is that clear? All right. So now denote by gamma of gamma star E. In other words, sections of the pullback, gamma star E. This will be the vector space of sections of E along gamma. Okay. So then we have the following definition proposition, which is called covariant differentiation along curves. okay, which says the following. There is a unique linear map, capital D sub dt, which goes from the sections of E along gamma to sections of E along gamma. Sigma goes to capital D sub dt of sigma, which satisfies the following. So first, it's a linear map, okay, a real linear map. And so it satisfies the Leibniz rule. So capital D sub dt of f times sigma is df dt into sigma plus f d sigma dt, okay, where f is a smooth function on the interval I, the interval of definition of your curve gamma. Okay. So this is the Leibniz rule. And secondly, if sigma is a section along gamma, which is given by composing a section of E with gamma, all right, then capital D sub dt of sigma is equal to nabla sub gamma prime t of S. Okay. So maybe I should draw you a picture. So you have your interval I, and you have your curve gamma. So this is some curve in the manifold. And then we're looking at sections along gamma. Okay, so that means for any point t in I, sigma t is going to be a vector in the fiber of E at gamma t. Okay. Okay, so this is a section along gamma. And then we have a map from sections along gamma to sections along gamma. Which is called covariant differentiation along gamma, which maps sigma to capital D sub dt of sigma. Okay. So this satisfies the Leibniz rule, right? D sub dt of f sigma is df dt sigma plus f capital D sigma dt. And it satisfies the following compatibility rule. It is compatible with the original connection on the vector bundle. Namely, if I take d sub dt of, if I take a section S composed with gamma, okay, see, this will be a vector field along gamma, right? Because see, gamma is going from the interval I into N. And then my section S is going into the vector bundle, right? So S of gamma of t, by definition of a section, this belongs to the fiber at gamma of t, right? So S composed with gamma, this is a section of E along gamma, right? So then it says if I take a section of E along gamma, which is of the form S composed with gamma, then to differentiate it, all I do is I take the tangent vector gamma prime here and apply the connection to S with respect to the tangent vector gamma prime t. Okay. So in this sense, this is the compatibility with the original connection. Okay. So is this clear? Yeah. So what this definition proposition is saying is that there is a unique such linear map, the covariant differentiation along the curve gamma, from sections along gamma to sections along gamma, which satisfies the Leibniz rule and the compatibility with the connection. Is that clear? Okay, so the main point is this compatibility with the connection. All right. That is what gives you the uniqueness. Okay. Any questions?
No, sir.
All right. Okay. So we first prove the uniqueness, and that will help us to prove the existence as well. Okay. So let's take an interval j and I, such that gamma of j is contained inside an open set U, where we have coordinates x1 to xn and a local basis of sections s1 to sk. All right. So we can do this by choosing j small enough, right? So that gamma of j is contained inside a nice open set U like this. Okay. So let sigma be a section of gamma along E, and let T naught be a point in J. So from the Leibniz rule, like we did earlier, it's easy to see that this d sigma dt at T naught, this only depends on the restriction of sigma to any neighborhood of T naught. Okay. So now let phi be a bump function on U such that phi is 1 in a neighborhood of gamma T naught. Okay. Then d sigma dt is the same as ddt of phi compose gamma whole squared into sigma near T naught, because both of these sections are equal near T naught. Okay. And the covariant derivative only depends on the values of sigma in a neighborhood of T naught. Okay. And sigma t I can write in terms of my local basis of sections as a sum over j, some coefficients aj of t into my local basis sj at gamma of t, right? So then right. So then if I look at phi compose gamma whole squared into sigma, then what I can do is this one phi compose gamma, I multiply with the AJs, and the other phi compose gamma, I multiply with the SJs. So this I can write as sum over J, AJ tilde into phi times SJ composed with gamma. Okay. Why do I want to do this? Because then my phi times Sj, this is now a global section on E, and my Aj tilde, this is phi compose gamma into Aj. This is a function on the whole interval I. Okay. Aj was defined initially only on the interval J, but now I've extended it to an Aj tilde on the whole interval I. Okay. So then by the Leibniz rule, we're assuming that this d sub dt satisfies the Leibniz rule. So applying it to this sum, this will be sum over j ddt of aj tilde at t naught into phi times sj at gamma t naught plus aj tilde at t naught into. So now by the compatibility property of the connection, this phi times Sj, this is a global section, right? So this composed with gamma, its covariant derivative will be given by applying the connection nabla in the direction of gamma prime T naught applied to this global section phi times Sj. Okay. And now this Aj tilde, since this phi composed gamma is 1 in a neighborhood of T naught, Aj tilde prime at T naught is the same as Aj prime at T naught, because they're both equal in a neighborhood of T naught. So this becomes Aj prime T naught into, and this phi composed, phi times Sj, phi is 1 near gamma T naught. So this becomes just Sj at gamma T naught, plus Aj tilde at T naught is the same as Aj at T naught. And now we use this other property of the connection that it only depends on the germ of the section near the point, right? So phi is 1 in a neighborhood of gamma T naught. So the germ of phi times Sj is the same as the germ of Sj near gamma T naught. So this will be nabla sub gamma prime T naught applied to Sj. Okay, so we can forget about the phi. And so what do we get? We get that therefore, if sigma, any sigma on the interval j, I can write as a sum over little j, Aj into Sj composed with gamma, right? In terms of my local basis Sj. And then what I find is that d sigma dt restricted to j, this has to be equal to sum over j, Aj prime into Sj composed with gamma, plus Aj into nabla sub gamma prime of Sj, right? This is what we just proved above, right? So this gives you the uniqueness of d sub dt, right? Yes? This proves the uniqueness of d sub dt, this covariant derivative, right? Any such linear map capital D sub dt has to be given by this formula, right? So that proves the uniqueness. Is that clear? Yes?
Yes, sir.
Okay. So that proves the uniqueness of the covariant derivative. And then for the existence, what you do is you cover the interval I by neighborhoods J1 to Jn such that each Ji maps under gamma into a nice open set Ui where we have a local basis of sections and local coordinates, okay, x1 to Sn, xn, and a local basis of sections Sij. And then for any section sigma along gamma, you define d sigma dt restricted to the interval ji by this formula star. Okay. Using on ji, you use the local basis Sij. All right. Okay. So for each I goes from 1 to n, we have on ui a local basis Sij. J goes from 1 to k. K is the rank of the vector bundle. Okay. So using this formula, we can define d sigma dt on the interval ji, right? Now you have to check that this is well defined on the overlap. Well, if I take two such intervals ji1 and ji2, then actually d sigma dt on ji1 has to equal d sigma dt on ji2. Why? Because the way we've defined ddt on ji, it satisfies the properties 1 and 2 on ji, right? Therefore, by uniqueness, ddt on ji1 and ddt on ji2 must coincide. Okay. Right, if it satisfies properties 1 and 2 of the covariant derivative, then we know it's unique, right? So then we'll get that on the intersection of these two intervals, ji1 and ji2, these two have to agree because they satisfy properties 1 and 2. Okay, so therefore by uniqueness they are equal. Okay, so therefore we get that d sigma dt will be well defined on the whole interval I. Okay, so that proves existence. Is this clear?
Yes, sir.
Okay. Yeah. So with respect to a local basis, this covariant derivative is given by this formula. Okay. All right. See, the point is that these functions aj, these are not functions on the manifold. They are functions on the interval I. Or well, or on a subinterval j of I. So, I mean, the point is any sigma, it is not necessarily of the form S composed gamma. It's not given by restricting a section of E to gamma in general, but locally, the point is, it is a sum of such. It's a linear combination of some SJs composed with gamma. Okay. It's a linear combination of sections of E restricted to gamma. Okay. Is the difference clear? You see what I mean? Okay, it may not itself be of the form S composed with gamma. All right. See, I mean, you can see that quite simply if your curve gamma is not 1-to-1, right? Suppose gamma has a double point like this. Okay. So then if I take these 2 points, say T1 and T2, which map to the same point, right? This P is equal to gamma T1 is equal to gamma T2, right? Okay. If I take a section sigma along gamma, such that sigma of T1 is not equal to sigma of T2, right? Then we cannot write sigma in the form S composed gamma for any S for any section S, right? Is that clear?
Yes, sir.
This S composed gamma, this takes the same values at T1 and T2, right? It just takes the value S of P. Do you understand? However, locally, we can write sigma as a sum over J, Aj of T into Sj composed with gamma of T. This we can do. We can write it as a linear combination of functions on the interval times restrictions of sections to gamma. Okay, but we cannot write it as one section restricted to gamma. That we cannot do. That's all I'm trying to say. Do you understand? Yes?
Yes, sir.
See, why do I want to write it in this form? Because after that, I can use the linearity and the Leibniz rule and the compatibility with the connection Labla. These properties will uniquely determine my covariant derivative d sub dt of sigma. Do you understand? Once I've written it in this form, then the compatibility with Nabla will uniquely determine d sub dt of sigma. Do you understand? So that's what we did here. Right? Okay. Okay, so we're more or less out of time. So let me not do more. Any questions? Any questions? Okay, so we've defined vector bundles and connections on vector bundles, and induced from a connection on a vector bundle, we've defined a covariant derivative along a curve, right? Of sections along the curve. Okay. So using this, next time we'll see how to define parallel transport in a vector bundle. Okay. Yeah, and we'll continue from there. Okay, so if there are no more questions, shall I stop? Yeah. Okay, so let me stop then, and I'll see you on Friday.